Hello, welcome to my talk on the history of aerodynamics, Part 2, the history of further explorations of aerodynamics in the 19th century and beyond. Here, the beyond is just a few years into the 20th century. The history of aerodynamics is not fully same as the history of basic fluid dynamics, basically fully established in the first half of the 19th century, the establishment of the Navier-Stokes equation. But the exploration in aerodynamics for developing flying machine was still ongoing, with the attempt to understand the generation of lift and drag on the flying bodies. It is interesting to see there was no much technology transfer from the general fluid dynamics to the field of applied aerodynamics before the 20th century. A good example is that the first use of Bernoulli's equation in the aerodynamic literature occurred in a paper published in October 1904. In this presentation, I will talk about the history in two different lines: the history of the theoretical aerodynamics and the fluid dynamics, and of the experimental aerodynamics or applied aerodynamics. In the first part, the main focus would be the establishment of the four fluid dynamics equation and the attempts for solving the fluid dynamics equation, especially on how to mathematically calculate the force, the lift of the flying bodies. Since Euler equation in 1757, it took more than 65 years that the researchers started to figure out how to include the fluid viscous force into the fluid dynamic equation. The first attempt was Navier in 1822, who employed the pure molecular force as the fluid viscous force for deriving the complete fluid dynamic equation. In 1827, Cauchy took the fluid as the perfect inelastic body and introduced the symmetric strain stress, which was adopted from his laws of motion for elastic bodies. In 1829, Poisson took the fluid as the temporary solid, together with the introduction of the pressure into the symmetric stress tensor. In 1834, Saint-Wallon used the concepts of molecular slides and approximations to derive the fluid dynamics equation. And in 1845, Stokes derived the four fluid dynamic equation by employing the Cauchy's symmetric stress tensor. His derivation is in a very similar form as we see in many textbooks. In 1934, Navier-Stokes equation was first named when Prandtl gave lectures on fundamentals of hydro and aeromechanics, according to the reference 2 here. Hermann von Helmholtz was a German physicist and physician, and he made his contributions to the modern aerodynamics. In 1858, he studied the difference between the irrotational and the rotational flows, and he could basically employ the concept of vorticity and vortex filament, vortex sheet to represent the feature of rotational flows. He could use the irrotational flows plus vorticities to represent the real flows. His more important contribution would be the three Helmholtz vortex theorems for the behavior of the vorticities in the inviscid fluid. The strength of the vortex tube does not vary with time. Fluid element lying on a vortex line at some instant could continue to lie on that vortex line. The fluid element, initially free of the vorticities, remains free of vorticity. He further studied the mathematical nature of the vorticity, vortex filament, and vortex sheet, which lead to the development of the so-called the surface of discontinuity in viscid fluid, which was published in 1868. In today's application, the physical thin boundary layer and the wake around an aerofoil can be expressed using the vortex sheet. For simplifying and solving the problem, see this picture here. As such, the viscous effect around the aerofoil can be included in the analysis of inviscid flows. Shortly after the Helmholtz paper in 1868 and the concept of the surface of discontinuities, some researchers saw this might provide a method for predicting the aerodynamic drag on bodies. So to solve the zero drag problem, the D'Alembert paradox, 1869, Kirchhoff first considered the force perpendicularly exerted on a flat plate, see here. From the picture, we can see a large region of dead air behind the flat plate. And for this, it can be understood the difference between the higher and the lower pressures on both sides of the plate would create a drag force on the plate. But Kirchhoff did not calculate the force for the case of the inclined plate. In 1876, Lord Langley, the 1904 Nobel laureate in physics for his discovery of argon, independently examined the same problem using the same concept, and he managed to obtain the normal force coefficient Cn given as this. This might not be correct in today's understanding, but it was a good attempt to mathematically calculate the fluid drag. In today's understanding, the flow pattern would not be correct, since in a small angle of attack, due to the fluid viscosity, the flow on the upper surface would be fully attached to the surface. Only in the cases of very large angles of attack, the flow on the upper surface would be fully separated. But it would be more complicated for the flow above the upper surface rather than the simplification as the dead air. Joseph Warrington Boussinesq was a French mathematician and physicist who proposed the Boussinesq's hypothesis on eddy viscosity. He actually reported the idea in 1872 and published it in 1877, in which he reasoned that the turbulent flow could be still represented by the averaged flow, but its viscosity, the artificial viscosity, would be greatly increased. A relation would be given as this as the Boussinesq hypothesis. But it must be noted, Boussinesq did not carry out the averaging as Reynolds did. It is well known today in the turbulence modeling. The expression for the Reynolds stress is often expressed as this. Here, K is the turbulent kinetic energy, and μT is the eddy viscosity. A misunderstanding here is the Boussinesq's eddy viscosity provided an answer for the Reynolds stress, but in fact, Boussinesq's relation appears 18 years earlier than the Reynolds stress, which was published in 1895. See the next slide. And Reynolds did not link the Boussinesq's eddy viscosity with the Reynolds stress tensor. According to Roddy from the reference 2 here, it was Prandtl who, in 1925, forcibly linked the Reynolds stress tensor and the Boussinesq's eddy viscosity together, a relation now being employed in most popular turbulence models. Osborne Reynolds was an innovator in the understanding of fluid dynamics, and in 1895 he employed the ensemble averaging approach for the Navier-Stokes equation, in which he gave the averaging calculation as this. Based on Reynolds, U bar here is the velocity of x direction at each instantaneous center of gravity of the fluid element, theta v. This expression itself might not be very physical, since the denominator sigma naught has no physical meaning. But if we time a constant theta v on both the numerator and the denominator, then we can see this averaging velocity is the momentum average velocity. And Reynolds gave the component moment or the specific moment of the component as this, so he obtained the expression for the velocity as the average velocity u bar plus the fluctuation velocity u prime. If we look at the picture at here, this is for an unsteady flow. So the average would be carried out on a short period t here. So the overall velocity would be still unsteady. And then Reynolds applied the averaging to the Navier-Stokes equation. And due to the nonlinearity of the Navier-Stokes equation, averaging the equation would lead an additional term, which is now named as Reynolds stress, given as this tau ij equaling minus u prime I and u prime j average. So this is the specific Reynolds stress tensor. Although the simple expression, this term contains all the turbulent information for the turbulent flow, and it causes the tremendous difficulties for solving the fluid dynamic equation. Ludwig Prandtl was a German fluid dynamicist and engineer. In 1904, Prandtl reasoned that at a large Reynolds number, which is true for many practical flows, the velocity transition from a certain value away from the wall to zero directly at the wall takes place in a thin layer, see the duct layer, which is named as the boundary layer by Prandtl. Accordingly, the fluid domain can be separated into two regions. The region away from the solid boundary, the flow viscosity can be neglected, or the viscous effect is much smaller than the eddy viscosity. Thus, the flow can be treated as the potential flows. The flow near the wall, a thin viscous boundary layer, in which the fluid viscous effect is important. So the boundary layer is a very useful concept, and this concept can be used for solving the problem. Like the Lambert paradox, the flow past the simple structure such as aerofoils and the wall functions. This is very useful in the modern CFD modeling, where near the wall boundaries, wall functions are often employed for numerical modeling, and the transition from laminar to turbulent, the boundary layer separation, etc. In this slide, Kutta-Joukowski theorem is discussed. In 1902, Kutta, in his PhD dissertation, first showed the possibility for calculating the airfoil lift using the mathematical formulation. For instance, for the Lilienthal's arc airfoil, he obtained the lift given in this form for this circular arc airfoil. Apply this to the Lilienthal's circular arc airfoil. It gives the lift coefficient as 1.047. This is for the 2D airfoil. Compared to the Lilienthal's data, the coefficient 0.381 in 3D from the experiment data. Even apply the 3D collection, Kutta's calculation would be still larger than the experiment data. And in here, the Lilienthal's data might be not so accurate. In 1906, Joukowski provided a complicated mathematical derivation to calculate the lift, gave the expression as this. The lift is proportional to the circulation of the fluid around the airfoil. This is the exact formula we can see in many textbooks. These two developments together form the Kutta-Joukowski theorem, which is often regarded as the fundamental theorem for the modern aerodynamics. This is especially true for developing the method for calculating the airfoil's lift before the CFD was used to solve the Navier-Stokes equation. According to the reference, the circulation theory of lift is still widely used today, as we see in the modern panel techniques for calculating lift values for airfoil in inviscid flows. Such technologies are still being revised and improved, and thus the circulation theory of lift is still evolving today, after more than 100 years since its first introduction. And based on the same reference, Langley was actually the first researcher who proposed the flow past an airfoil can be expressed as the uniform flow past the circulatory flow. Langley presented the idea in 1897, but the idea only appeared in his popular book, Aerodynamics, which was published in 1907. The second aspect is the experimental aerodynamics or fluid dynamics in the 19th century. This is especially important for applying aerodynamics or fluid dynamics, since many pioneers sought all different ways to make the heavier-than-air flight possible. Although the fluid dynamics equation was fully established in the first half of the 19th century, solving the question was impossible. Thus, the experimental aerodynamics became the only way for solving many practical problems. In the introduction for George Cayley, he was an English engineer, inventor, and aviator, not an aerodynamicist. The reason for this is that he contributed little to the theoretical aerodynamics. Even he used both flight tests and lab experiments to gain an understanding of the basic aerodynamics. Cayley formed the series measurement of the variation of lift with different angle of attack to show the emphasis on the aerodynamic lift, while other researchers might only be interested in drag. Cayley's basic concept of mechanism of lift on a flexed wing was totally different from the mechanism of propulsion, like the Da Vinci's eddy screw helicopter. This is a large leap in the advancement of the technique aeronautics. Cayley was the first to appreciate the benefit of the cambered lifting surface for creating more lift for the fixed-wing flight. Cayley's idea concerning the drag on different components on the vehicle, like the drag on the wings, drag on the fuselage, which were quite consistent with our modern conception of the parasite drag and the induced drag. In 1871 in Britain, Francis William, following the unsatisfactory experiment with the Whirling-arm, in which the moving air with the Whirling-arm made the airspeed measurement very difficult. So he persuaded the Aeronautical Society of Great Britain to raise the funds to build the world's first wind tunnel. This wind tunnel had a depth of 12 feet, 3.6 meters, and the work section 18 inches times 18 inches, which is 0.47 meter times 0.47 meter, and the airspeed is 40 miles per hour, about 18 meters per second in the cross-section. In today's terminology, this wind tunnel is an open-jet wind tunnel. Although the poor flow quality, the tests carried out in the wind tunnel could show two significant results. At a small angle of attack, the lift force varies in proportional to the sine of the angle of attack, rather than the square of the sine, which was indicated by Newton. The wings of high aspect ratio had higher lift to drag ratio, L over D, than those of low aspect. In the early 1880s, also in Britain, Horatio Phillips built a wind tunnel of similar proportion, but with a steadier flow. Using this wind tunnel, Phillips could develop and patent a series of cambered modern airfoil. See the pictures here. And for the importance of the wind tunnel, the Wright brothers made an important decision in 1801 to build their own wind tunnel and test their wings rather than use the existing data, which was an decisive step which resulted in the initial successes of the 1902 glider and the huge success of the first heavier-than-air flight in 1903. In earlier 1880s, Reynolds performed a serious experiment of flows in pipes of different sizes to examine the phenomenon of the flow from laminar to turbulent transition. In the data analysis, Reynolds used the different combinations of the physical parameters, and he could finally conclude one non-dimensional parameter he named the K number in his publication in 1883. This number can be used to indicate the transition from laminar to turbulent, and this K number was later named as Reynolds number. And in the publication in 1895, he showed the experimental result. For the laminar flow, the Reynolds number is smaller than 1900. Reynolds used the stable flow in the paper for the laminar flow, and when the Reynolds number is more than 2000, the flow becomes turbulent. Reynolds used unstable flow in the paper. This experimental result is quite close to the result from what we take today as the critical Reynolds number, 2300. In today's understanding, Reynolds number becomes a very important parameter for studying the flow phenomenon. And from the dimensional analysis, the fluid pressure, lift, and drag can be all the function of the Reynolds number, and the expressions of these aerodynamic forces would be normally given in the non-dimensional form as the Reynolds number itself. Otto Lilienthal was a German pioneer of aviation as both researcher and practitioner in aviation. Lilienthal, as a researcher, had been tested airfoil with the Whirling-arm device and later obtained the data from the outside in the wing. He built the first set of the data in applied aerodynamics and plot the data in a systematic fashion, the drag polar diagram, which respected the basic rules of the fundamental fluid dynamics. The dataset was later used by others, including the Wright brothers, who designed their 1900 and 1901 gliders. Lilienthal's more important contribution would be the applied aerodynamics, in which he played the other roles: inventor, builder, and pilot of the first practical gliders. He himself had made more than 2,000 glider flights, and for which he lost his life in 1896. Lilienthal's successes in the glider flight had significantly inspired both Kutta, through his PhD supervisor, and Joukowski for developing their mathematical models for predicting the lift of the airfoil. Now we know the Kutta-Joukowski theorem, the last piece of the mystery aerodynamics in understanding the heavier-than-air flight. Samuel Pierpont Langley was an American astronomer, physicist, and aviation pioneer. Langley had begun a series of aerodynamic experiments in 1886 on a large Whirling-arm device, and the test data has been reported in his book, Experiments in Aerodynamics, which was published in 1891. This was the important American contributions to the aerodynamics in the 19th century. Langley's contributions to aerodynamics in both science and the engineering aspect. He explored the basic physical laws of aerodynamics and demonstrated scientifically the practicability of the powered heavier-than-air flight. And he designed a series of flight machines in order to confirm his conclusions from his Whirling-arm data. See this picture, the flying machine. And based on the reference, Langley's most interesting and most controversial conclusion from his experiment data was the Langley law. The power required for a vehicle to fly through the air decreases as the velocity increases, which was based on his soaring measurements for velocity less than 20 meters per second. The conclusion was wrong when compared to the practical applications. Langley's contribution to aerodynamics earned him the name such as NASA Langley Research Center, Langley Air Force Base, and some other names. In the last slide of the talk, the Wright brothers' fliers would be introduced. In 1896, the legendary Wright brothers began the interest in the flying machine, but the serious study of the important information did not begin until 1899. In August 1899, the Wright brothers constructed a small glider which incorporated a wing wrap technique for the larger control. They invented this control technology. In 1900 and 1901, the brothers used the existing aerodynamic data in the design of their gliders, but with no success. In 1901, after the test season, they were disappointed and discouraged by the flight result. So they made the comments such as, "Man would not fly for another 50 years." And another version would be, "Not within 1,000 years would man ever fly." In 1901, they built their own wind tunnel and started their test program in 1901 and 1902. This was the most important decision they made, which led to the new remarkable success for glider in 1902. And on December 17, 1903, the Wright brothers' flyer lifted into the air and flew for 12 seconds, covering 120 feet over the ground in a headwind. This is a truly heavier-than-air flight in the aviation history, in which the relative airspeed is about 14.9 meters per second. But the ground speed is about 3 meters per second. And after that, more successful studies. For example, less than a year, in 1904, a 4 closed-circuit flight was made, covering 1,244 meters in 1 minute 30 seconds, with the average speed 13.8 meters per second. And more successful studies. This will be discussed in my next talk.